Hey guys, welcome back to CCL Biology, the channel for easy to understand biology lessons. If you're looking for help with general, AP, or even college introductory biology, you are in the right place. I am your friendly biology nerd. Thank you so much for tuning into my channel. In this video, I'm going to be talking about macromolecules or biomolecules. So if you want a better understanding of macromolecules, then stay tuned. While you're here, don't forget to click the like button and comment below if you find this video to be helpful. And if you want more easy to understand biology lessons, then be sure to subscribe to my channel and click the notification bell to get updates for new videos that go up every week. Okay, this video is about macromolecules or biomolecules. We're going to talk about what they are, how they're formed, and how they're broken down. I'm going to do separate videos for each of the 4 individual macromolecules. This video is just more of an overview of macromolecules in general. So first off, let's look at this word, macromolecule. It's really just what it sounds like, a big molecule. Now, a molecule is a chemical substance that's made of 2 or more atoms that are joined with covalent bonds. Be sure to check out a previous video that I've done about molecules. I'll link that in the description box below. But with that being said, a macromolecule is just a big molecule or a big chemical substance that's made of several units, smaller units, that are covalently bonded. But what makes this molecule so macro? It's the number of units. Macromolecules can have hundreds or even thousands of units. Macromolecules or biomolecules are grouped into 4 categories. We have carbohydrates, lipids, proteins, and nucleic acids. Some people don't technically consider a lipid to be a macromolecule because it's built differently than the other 3, which I'll talk about more in this video. But for the most part, lipids are generally accepted as macromolecules. Now, these are also called biomolecules because they're mostly responsible for the structures of living organisms. They help construct cells, tissues, and organs. Macromolecules provide energy, structure, protection, and genetic information, among many other things. Now, each of these 4 groups is very different from the other in terms of its basic structure and function, aka how it's arranged and what it does. But there are some similarities among these 4 groups, including the atoms that they use, the process by which they're built, and the process by which they're broken down. So let's talk about each of those 3 similarities individually. All 4 macromolecules have the same 3 constituent atoms: carbon, hydrogen, and oxygen. Carbon and usually hydrogen are 2 atoms that exist in any organic compound, and that's what a macromolecule is. It's an organic compound. So think of those 3 atoms together, carbon, hydrogen, and oxygen, as CHO. And shout out to the Amoeba sisters for these abbreviations that I'm going to be using. So carbohydrates and lipids are always going to have that CHO combination. They have carbons, hydrogens, and oxygens throughout their structures. Now, in addition to CHO, carbon, hydrogen, and oxygen, proteins also are always going to have nitrogen. So we'll call this CHON for carbon, hydrogen, oxygen, and nitrogen. And in addition to CHON, nucleic acids are always going to have phosphorus. So we'll call this abbreviation CHOMP for carbon, hydrogen, oxygen, nitrogen, and phosphorus. So the basic makeup of the macromolecules sounds like CHO, CHO, CHON, CHOMP. And again, credit to the Amoeba sisters for those abbreviations. Sometimes macromolecules will have additional atoms like sulfur, but this CHO, CHO, CHON, CHOMP shows you the elements that are always going to be there. Now let's talk about how macromolecules are built. Macromolecules are polymers. If we break down the word polymer, we get a simple definition: poly meaning many, and the mer meaning unit. So a polymer is something with many units. And again, that's what a macromolecule is. Polymers are long chains that have identical or very similar molecular units. Think of it like a string of pearls or cars on a train. Each individual pearl or train car is called a monomer, meaning one unit. Monomers can function on their own, but they can also link up with other identical or similar monomers to make polymers. Each macromolecule has a different type of monomer. So let's take a look at each of the 4 different types of monomers. Now here, we're looking at a piece of a carbohydrate macromolecule. Now you see 3 funny looking shapes that kind of repeat themselves, right? So these are 3 monomers or individual units of a carbohydrate polymer. Now the name of this monomer is a monosaccharide. Again, we get that mono in there, meaning one. Saccharide comes from the Greek word for sugar. So an individual unit of a carbohydrate is a sugar. So these are 3 monosaccharides or 3 sugars that we're looking at. Again, the monomer of a carbohydrate is a monosaccharide. Next, let's go down here. So here we're looking at 1 unit or a monomer of a protein. Now this monomer is called an amino acid. So 1 unit of a protein polymer is an amino acid. This is also called a peptide. So you can hear one or the other, amino acid or peptide. They're both talking about the monomer of a protein. All right, next, if we come over here, we're looking at a monomer or an individual unit of a nucleic acid. Now, notice there are 3 parts here. They have 3 different colored sections, but this whole thing is 1 monomer. This is 1 unit. So the monomer of a nucleic acid is called a nucleotide. So this is 1 nucleotide here. Now down here we get to lipids, which again are a little funny because they don't really have 1 individual unit, kind of like these other 3 per se, but we do break lipids down into triglycerides or triacylglycerols. 2 names, same thing. So again, even though lipids don't technically have monomers, which is why they're technically not really considered polymers, the closest that they get to a monomer is a triglyceride or triacylglycerol. Now, as I said earlier, each of these individual monomers can function on its own. So what do I mean by that? For example, if we go back to this piece of a carbohydrate polymer, we see 3 monomers, 3 monosaccharides or sugars. Now this monosaccharide can function on its own. It has all the properties and characteristics of a sugar. It's going to do whatever a sugar can do all on its own. It doesn't have to be linked up in a polymer to have some type of function. Same thing here with a nucleotide, with an amino acid, and even with a triglyceride. Each of the monomers can function on their own. But let's talk about how monomers link up with other similar monomers to make those polymers. The monomers of carbohydrates, nucleic acids, and proteins form polymers in the same way. Now, lipids have a different process by which they're built, which again is technically why they're not considered macromolecules. But the process by which monomers connect is called dehydration synthesis, or a dehydration reaction. Now, let's break that down a bit because that can seem like a lot. Synthesis means to create something. So in other words, it's a dehydration creation. Now, what do you think about when you hear the word dehydration? A lack of water, right? Well, this reaction does result in the loss of a water molecule, H2O. Now, every monomer contains carbon, hydrogen, and oxygen. Remember, we talked about that earlier with CHO, CHO. But in order for one monomer, like a monosaccharide, to bond with another monosaccharide, one of those monosaccharides has to give up a hydrogen, and the other monosaccharide has to give up a hydrogen and an oxygen, or a hydroxyl group, OH. Be sure to check out my video on chemical groups to know what I mean when I say hydroxyl group. So because one monosaccharide is giving up hydrogen and the other is giving up oxygen and hydrogen, we're losing HOH, or H2O. So this is what I mean by a loss of water. It's not like there's a literal drop of water that falls out somewhere whenever this reaction takes place, but we're losing the equivalent of a water molecule, 2 hydrogens and an oxygen. So let's take a look here to see how this actually works. So here we've got an illustration and we've got these purple circles. This is representing a polymer, a short polymer, of course, because as we said, polymers typically have hundreds or thousands of units. So each of these numbers represents a monomer. All right, so here we have 3 monomers represented by the 1, 2, and 3 to make our short little polymer. On one end of this polymer, we see an OH or hydroxyl group. On the other end, we see a hydrogen. Okay? Now, to be clear, each of these monomers, monomer 1, 2, and 3, each of them have their own individual OH on one end and H on the other. This one had an OH here and an H there, and this one had an OH and an H there. But now, let's see what happens when another monomer wants to join in and connect right here next to this monomer number 3. So here we have an unlinked monomer, again represented by this unnumbered purple circle. And as you can see, it has its OH and its H. And let me pause here because you may be saying, hey, I thought all macromolecules have carbon, hydrogen, and oxygen. Where's the carbon? The carbon is kind of represented by the purple circle itself. Remember, carbon is usually not, the C is usually not written just because it's understood that the skeleton is made of carbon. All right, so there's carbon, and we're going to say that's here in the purple circle. And then we see the hydrogens, we got 2 there, and the oxygen. Now, in order for this monomer unit to join in with these 3 and make this polymer longer, we have to have a dehydration. We have to remove this OH, this hydroxyl group here, and this hydrogen. Once we do that, that's going to allow this carbon skeleton to bond to this carbon skeleton number 3. All right, so as it says, the dehydration is going to remove that water molecule, so bye-bye H2O, and that's going to allow this unit to bond to monomer number 3, forming a new bond. So now where we had 3 monomers before, now we have 1, 2, 3, 4, all right? So still a really short polymer, but longer than it was before. So here it's illustrated with some monosaccharides. You don't have to pay attention to all this craziness going on. Let's just look here at what's in the red. So here on this monosaccharide, we see the hydroxyl group that's highlighted for us in red. And we have another monosaccharide, so that's the plus sign there. And it also has hydroxyls and hydrogens and all the same other atoms that are here, but we're highlighting the hydrogen on this particular one. So in order for this monomer number 2 to connect or bond with monomer number 1, we're going to remove the OH from here, and we're going to remove this hydrogen. All right, so let's see what happens. So this arrow shows this is the reaction happening. This is the dehydration synthesis. All right, now we see these 2 monomers have been joined together. Now, as you can see, they're joined right here. So let's see exactly what happened. Now, if we pay attention to this monomer, all right, it was this hydroxyl group, this OH right here, that was removed. So when we go to the other side, we shouldn't see this OH here. All right. And here for this monomer, it was the hydrogen that was removed. So we should see this gone. All right. This oxygen here that's still in black is left behind. So we should still see an oxygen in between the 2 monomers. If we come over here, that's exactly what we see. Okay. So we see these 2 lines slanted toward each other, showing that the 2 monomers are joined. And we have this oxygen in the middle. This is the oxygen that was left behind. Notice the hydrogen is gone, and here the hydroxyl group is gone. But since atoms and elements and really almost kind of nothing for that matter just disappears into thin air, that water had to go somewhere, so we see it here. All right, plus H2O. So what this is saying is that these 2 monomers join together by getting rid of or by removing the H2O. So now they're linked and the H2O is left over here at the side. Now this reaction took us from 2 individual monomers to what we call a diomer. Okay? And diomer, if you hear the prefix di, which means 2, that just means something with 2 units, as opposed to a monomer with 1 unit. Now, if we add another monomer to this diomer with another dehydration synthesis, then we'll get 3 monomers. Anything greater than 2 units is called a polymer. So that's why here we can officially call this one a polymer because it has 3 units. So we go from monomer to diomer to polymer. So each time that we want to add a monomer to our polymer chain, we have to have a dehydration reaction. That means to build a macromolecule, which can have hundreds or thousands of monomers, we're going to get a lot of dehydration reactions. And we can actually count the number of dehydration reactions since monomers are discrete units. If n equals monomers, then there are n minus 1 dehydration reactions that had to take place to build the polymer. Now, for instance, let's say we have a polymer with 30 units, 30 monomers. That means that we had 30 minus 1, or 29, dehydration reactions that had to take place to build that 30-unit polymer. Now let's look at the reverse, breaking a polymer down into individual monomer units. But first off, why would we want to do that? Why would a polymer need to ever be broken down? Well, most organic polymers that enter our bodies are too big to enter our individual cells, so they have to be broken down. I'll talk more about that in upcoming macromolecule videos. But here, let's just focus on the reaction that is used to break a polymer down, and that's called hydrolysis. Now let's look at this word, hydrolysis. Hydro means water, and lysis means break. So, water break? Are we breaking water? Well, not quite. The water is doing the breaking. The water is breaking the bonds in between the joined monomer units to separate them. Now, in the dehydration synthesis, we saw a water molecule being removed in order to bring 2 monomers together. Here, with hydrolysis, we're going to have the opposite. We have a water molecule that is added in between 2 monomers to break the bond in between those 2 monomers. One of the hydrogens in the water molecule attaches to one of the monomers, and the hydroxyl group, or OH, attaches to the other monomer. Now again, this is not like a literal drop of water, but it's the equivalent of a water molecule, 2 hydrogens and an oxygen. So here we have a similar illustration like we saw with the dehydration synthesis. I've got a short polymer with 4 identical joined monomer units, represented here 1, 2, 3, 4, of course. And we see the hydroxyl group here on this one and the hydrogen here. So just to backtrack to the dehydration, in order for monomer 2 to join to monomer 1, monomer 3 to join to 2, and 4 to join to 3, each of them had to give up a hydrogen while the other gave up a hydroxyl, or an OH. So this 4th monomer gave up its hydroxyl group, its OH, to join with 3, and kept its hydrogen. Whereas this first one, in order to join with unit 2, gave up its hydrogen and kept its hydroxyl. So just to clarify that a bit. But now what we want to do is break this polymer apart into individual monomer units. So in order to do that, we're going to add our 2 hydrogens and an oxygen to break the bond where we want to separate the polymer. So hydrolysis adds a water molecule. So we see the water molecule coming in, and what's going to happen is we get hydroxyl that's going to bond to this monomer carbon skeleton here, and the hydrogen is going to bond here to monomer 3. So now we've broken the bond between monomer number 3 and monomer number 4. So now we have a 3-unit polymer and an unlinked monomer. Now, if we want to separate monomer units 2 and 3, we have to have another hydrolysis. And if we want to separate monomers 1 and 2, we have to have a 3rd hydrolysis. So just like with the dehydration reaction, for every breakup that you want to have, you need to have a hydrolysis reaction. So if you have n number of molecules, you're going to have n minus 1 hydrolysis reactions. Okay, so now let's look at the reverse of the illustration that we saw earlier here. Here we've got a disaccharide, meaning 2 sugars. Remember, a monosaccharide is the monomer of a carbohydrate. So here, since we've got 2 joined monomers, or 2 joined monosaccharides, we have a disaccharide. Now, we want to break them up. So they're joined here. You see this oxygen here. So in order to break them up, we have to add H2O. So we see the disaccharide plus H2O, and what that gives us, and remember, let's follow the red here, one of the hydrogens joined here to monosaccharide number 2. The other hydrogen and the oxygen, or the hydroxyl group, joined the first monosaccharide right here. So that broke the bond that was illustrated here. That broke the bond and now gives us 2 individual monosaccharides. Well, that's it for today's video. I hope it was helpful for you. If so, then be sure to leave a thumbs up in the comments section below. And if you have any remaining questions, be sure to type those below and I'll do my best to give you an answer. Don't forget to like, comment, and subscribe for more easy to understand biology lessons. Thank you so much for watching CCL Biology. That is Christ-Centered Life. God bless and bye-bye.